Dr. Michio Kaku, theoretical physicist, futurist, and father. Harvard at 17, PhD at Berkeley in 72. Kaku has had more than 70 articles published in physics journals such as Physical Review, covering topics like superstring theory, supergravity, supersymmetry, and hadronic physics. He is Superman, essentially. His books, Physics of the Impossible, Physics of the Future, and The Future of the Mind became New York Times bestsellers. His new book, The God Equation, takes us through the quest for the theory of everything, which is already a bestseller in the US and the UK. So congrats on that, Dr. Kaku.
Well, thank you.
Great. Well, I would like to first start off, and let me make sure I'm recording just to have a backup here. I want to start off with a question maybe you don't get a lot. I would like to first touch on what I would imagine has been the greatest and perhaps most rewarding adventure of your life, fatherhood. And let me throw a quote at you from your daughter Michelle from a Fatherly piece that she wrote. And she says, looking back, I think explaining the complicated ideas behind these projects to us as kids helped him to figure out how to communicate about science to the masses. When you hear this quote from Michelle, where does it take you?
Well, it takes me back as a youth, because now I get a lot of emails from children, and they want to know about all the fantastic things they see in the movies: hyperspace, antimatter, warp drive, black holes. And I have to be able to explain these concepts to them, just like I had to be able to explain these concepts to my children. And I go back to when I was 8 years old, because that's when it all started. When I was 8 years old, a great scientist had just died, and all the papers flashed a picture of his desk. That's all, just a picture of his desk with an open book. And the caption said, "This is the unfinished manuscript of the greatest scientist of our time." Well, I was hooked. Just like the children that emailed me today, I was hooked. I had to know what was in that book. Why couldn't he finish it? What's so hard? Why didn't he ask his mother? It's a homework assignment, right?
Yeah.
Well, then I went to the library and I found out that this man who just died, his name was Albert Einstein. And that book was the unified field theory, the God equation, an equation perhaps no more than 1 inch long that would allow us to read the mind of God. So when I talk to children, I want to convey to them the same excitement, the same flush of discovery that I felt when I was a child. And then when I was in high school, I took it one step farther. I went to my mom and I said, "Mom, can I have permission to build an atom smasher in the garage? A 2.3 million electron volt betatron particle accelerator?" And my mom said, "Sure, why not? And don't forget to take out the garbage." When I took out the garbage, I assembled 400 pounds of transformer steel, 22 miles of copper wire, and I built a betatron accelerator in the garage. Every time I plugged it in, I would blow out all the circuit breakers in the house. And my poor mom, she'd shake her head and say, "Why couldn't I have a son who plays baseball? Maybe if I buy him a basketball. And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these machines in the garage?"
Yeah.
Well, that got me accepted to Harvard, but my scholarship there was paid for by Edward Teller, father of the hydrogen bomb. He knew what I was doing, so he offered me a scholarship. After I graduated from Harvard, he offered me a job to design hydrogen warheads. Well, I politely declined the offer, very kind offer, because I wanted to work on something even bigger than a hydrogen bomb. I wanted to work on creation of the universe. So in other words, I want to convey to young kids the excitement, the drama about being able to understand the laws of the universe. I like to think that on the other side of the Milky Way galaxy, there's an alien scientist with different notation writing the same equations, the same concept on the other side of the galaxy. That's what I hope.
Interesting. So what if your mother would have said no? you can't build this crazy atom smasher in the garage. What do you think that were you the kind of kid that would have just done it anyway, or were you pretty obedient? You would have maybe had to find a different location, or
I would have told my mother, how many times do I have to sweep the floor? How many times do I have
make
to
a
pick up the
deal.
garbage?
Yeah,
Make a deal.
that's smart. So, speaking about fatherhood for a second, and then we'll get straight into physics. How do you determine what it means to be a good father? And another way to put that is, how would you describe your moral foundation?
Well, I like to think that there really is a meaning of life for all of us. And the meaning of life is not to be given to us by some guru from a mountaintop. We have to struggle to create our own meaning. And that's what I tell young kids. The world is not a piece of cake. Meaning is what you make of it. You have to struggle. It's too easy. It's too easy to have the meaning of life given to you. You have to work for it. So the meaning of life is to struggle to find your own meaning. So I tell kids, find your own path. Find your own way. What excites you? What gets your blood going? What motivates you? And go for it. And, when I was a little boy, there was a pamphlet I still remember in elementary school. And the pamphlet said, so you want to become a physicist? And they ask a question. What does a baseball player and a physicist have in common? I said, gee, I don't know. What does a baseball player and a physicist have in common? And the answer is they both get paid to do what they love. And I said to myself, wow, that's for me, getting paid to have fun.
Yeah.
I mean, what could be better than that? Getting paid to have a great time.
Yeah, it seems like that's a lot of behind a lot of drives for people in their career, what people wish to be doing. Like they can't even imagine being able to stay home and do something they love, or go somewhere where they cannot wait to get to work. But that seems to not be the reality that everyone lives in for the most part. But it is a kind of a universal drive.
Yeah, when I was in college, it was kind of fashionable to have an identity crisis. Who am I? What am I doing here anyway?
Yeah.
And sometimes people would have a nervous breakdown and they would lose a part of their life searching for themselves. What am I doing? I had the joy at a very young age of knowing I wanted to be a theoretical physicist.
Right.
I didn't know what the word was. I didn't know what the concept was. I just knew that is what I wanted to do when I grow up.
Right.
And that was a gift. That was a rare privilege because I get paid to have fun. Doing this is fun.
Yeah.
And my attitude is, yeah.
Oh, I was going to say, I kind of share that. Like, I've always been interested in the questions that people would point to say, that will never be answered, or this cannot be answered, this cannot be done. And then I think of engineering and I try to imagine how things could be done that people are saying that they can't be done. So that fundamentally got me interested in the scientific method and into physics. Definitely.
Right. And I like to think of the universe as a chess game. Over thousands of years, so many people have figured out how the pawns move, how the bishop moves, how the king moves. But now we want to find out the rules of the entire game of chess. That's the God equation, you see. And we want to become grand masters. And it's a joy trying to figure out these pieces, how these pieces move, because that's what the universe is. And I think that's our destiny. Our destiny as humans on the earth is to become grand masters of the universe.
Okay, now I can't wait any longer. We got to get into physics. Before we dive into your new book, we must address this breaking news from Fermilab's G-2 experiment. We have an anomalous G factor that's popped up, which for everyone, which is the magnetic dipole moment of the muon. The G factor is a measure of the muon's strength while interacting with the magnetic field. So what could this anomaly mean, Dr. Kaku?
This is huge. This is really huge. For 50 years, think about it. For 50 years, we've had this clumsy theory, ugly theory called the Standard Model of particles, but it works. You can't go against it. After World War II, we started to split apart the proton. And we thought things would get simpler the deeper you go. We found hundreds of subatomic particles. And J. Robert Oppenheimer, the father of the atomic bomb, he once said, and I quote, "The Nobel Prize in Physics should go to the physicist who does not discover a new particle this year." Because we were drowning in subatomic particles. Now we have a little bit of order, the standard model, but it is ugly as sin. 36 quarks and antiquarks, 20 free parameters that are adjustable, 3 identical copies or generations of particles. I like to think of it as taking an aardvark, a platypus, and a whale, scotch taping it together with scotch tape and declaring it, aha, this is nature's finest evolutionary achievement, the grandest pinnacle of evolutionary theory. Well, the standard model is a theory only a mother can love, but that's why for 50 years we've been looking for a deviation, a slight crack, because that would signal a higher theory. A higher theory, maybe string theory. But that's what we've been looking for, and we never found it until 2 weeks ago. After 50 years of wandering in the wilderness, we finally found a crack, and that could signal new physics, perhaps string theory. And that's why a lot of us are very excited by this.
Right. And for anyone that's interested, the G factor is supposed to be approximately 2 in the muon, but we have a result of 2.0011596521811643 is the number that's being tossed around. So to the layman that might seem like, well, what's the big deal? But it's an anomaly, and even small anomalies could, like you said, Dr. Kaku, maybe there's a extra gauge boson out there that we haven't identified yet, or maybe there's something else that's being interacted with. It's quite exciting.
It's very exciting, realizing the fact that the magnetic property of the muon should be identical to that of the electron. The electron has a partner, the muon, and they should have identical properties according to the standard model. But looking at the magnetic properties of the muon, we find that it's different, much more different than it should be, and we're scratching our heads.
Right.
In other words, there's got to be a new particle out there. And we think, that we cannot prove, there could be a new symmetry out there governing these new particles called supersymmetry. And supersymmetry is the symmetry of the string. So it's too early to say for sure, but there's a lot of excitement. The drum rolls are beating now. Now people are wondering, could this be it? Could this be a clue that there is a fantastic new theory out there? That's what's driving all the excitement.
Right. And the muon is quite massive. Does that have is that any indication of why it might have stumbled upon this probabilistic interaction?
Well, the muon is identical to the electron, identical, except it weighs more and it decays differently. Other than that, they are twins. But this new result shows that they're not twins at all. This new result shows that the magnetic property, the G-2 of the muon, differs from that of the electron, and that's not the way it's supposed to be.
Right.
Standard model has survived all challenges for 50 years until 2 weeks ago. And that's why people are scratching their heads and saying, aha, there's a Nobel Prize out there waiting for the people who can figure this out. Now, I have a word of advice. If any of your listeners ever figure this out, what should they do? I give them advice. First, tell me first. And we'll split the Nobel Prize money. You and me will split the Nobel Prize together.
Okay, that's a good deal. I agree. Now, and since you bring that up, how important? Because I was listening to some of your early interviews in your career. How important are young minds, young fresh minds, coming into the field of theoretical physics?
I think young fresh mind is the fuel, the rocket fuel that makes the rocket take off. I mean, it's no accident that many of the Nobel Prize winners were quite young, 21, 22, 23. Who founded quantum mechanics? People like Dirac when he was 20-something, Heisenberg. They were like children. But why were they so successful? Because when you get older, you have committee meetings to do. You have to talk to a lot of students. You have reports to make. When you're young, You got no distractions whatsoever. It's just you and that blank sheet of paper. Well, when you're famous and influential, you're on committees, you have to have a schedule with airplane flights everywhere. I mean, it's distracting. And that's why I think the young people are fresh, and they don't mind challenging the powers that be.
Right.
See, Einstein had nothing to lose, absolutely nothing to lose, because he was not even a practicing physicist. He couldn't get a job. Think of that.
Yeah.
In fact, at one point, he tried to sell insurance. Could you imagine opening the door and there's Albert Einstein trying to sell you life insurance?
He might have an upper hand on the IQ scale
Yeah,
in most situations. Okay, now let's get into the book. Your new book, The God Equation. Before we get into the meat of it, let's talk about the title. So my question about the title is, why invoke a label like God in a science book, a label that is riddled with seemingly unlimited subjectivity?
Well, first of all, the God equation concept is not new at all. In mathematics, there exists a God equation for the last 150 years. Euler was the one who wrote down the mathematics God equation, which unified the constants of math. 1, 0, pi, square root of minus 1. One equation unifies all the constants of mathematics. Now, this is pure math. It has no practical application whatsoever. But think about it for a moment. If you had a God equation for physics, you would unify not just 1 and 0 and pi. You would unify the nuclear force with gravity and the weak force. That's huge.
Yeah.
Because that governs the Big Bang. That governs the creation of the universe. And where do you find it, the creation of the universe? Some God of some sort. So the Higgs boson is called the God particle. But the God particle, of course, was very important at the beginning of time, but it obeyed an equation. There was a rule to the Higgs boson. The Higgs boson, by the way, won the Nobel Prize for the physicist who proposed it, a Nobel Prize for the God particle. But now we're talking about the whole ball of wax, everything, the equation that governs the God particle.
Yeah.
That's what all the excitement is about.
So yeah, and I think the critique about invoking God would be, this term. A lot of people take it to mean something connected to their personal God or their, the way that they think about this term, kind of like love. We all have a different interpretation of what love is. So some might say maybe it's better to just stick to calling it, the grand unifying theory, because some people might take it to mean that you are one step closer to demonstrating that, their mythical God actually exists.
Well, we are talking about creation. We are talking about Genesis. We're talking about why we are here. We're talking about the ultimate question. You realize that for 2,000 years, the greatest minds of the human race have grappled with the question, is there a theme? Is there a single principle? Is there a fine paradigm that explains everything we see around us? And that is the God equation. And even the Greek philosopher Pythagoras came up with the unifying paradigm to explain everything. And that was music. He thought only music had the complexity to describe all the stars, all the planets, all the richness of the universe. Today, we have revived that theory. Pythagoras' theory of music is now string theory, which we think governs the creation of the universe itself. What is the purpose of God? The purpose of God was to set the universe into motion. That's why we want to quote, read the mind of God. And these are Einstein's words. Einstein once said that science without religion is lame. Religion without science is blind, but they complement each other.
See, I'm not. It's interesting to me. The God term and religion. These are artistic formations as far as I can see them. Artistic, creative formations of humanity. And I sit in the atheist position where I haven't seen sufficient demonstration to believe that there are any God creatures of any kind or creators. But I don't make the positive claim that there are no gods. I wouldn't want to adopt that burden of proof. But so I guess maybe the God term or label isn't as universal as it may have been back in the time of Pythagoras. So it's that's where the question comes from
Well,
me.
a few years ago, the God letter was up for auction. It was on an auction house. Einstein wrote a letter where he laid out his position on God. That letter shocked people. It sold for millions
Oh,
of
I bet.
dollars.
Yeah.
A throwaway letter where Einstein talks to his friend about God sells for millions of dollars because
Yeah.
people really are curious. Now, Einstein did not believe in a personal God, a God that answers your prayers, that smites the Philistines, that walks on water. No, God, he did not believe that God created the universe just so you can get a bicycle for Christmas. That's not the personal God that he believed in.
Right.
He believed in the God of order, the God of Spinoza, the God of elegance, simplicity. The universe could have been ugly. It could have been random. It could have been chaotic. It could have been a mist of electrons and neutrinos. But here we are.
Yeah.
Here we are with this gorgeous universe. I could put all the laws of almost everything on one sheet of paper. On one sheet of paper, I could put Einstein's theory, about an inch long, and the standard model, which is about, a foot long. But there it is, the theory of almost everything on one sheet of paper. Now, how about that? It didn't have to be that way, right? It could
Mm.
have been chaotic, messy, random. It could have been just nonsense. But here we are with consciousness, talking about love, talking about order, simplicity, elegance. I mean, Einstein thought of himself as a little boy walking into a library, a huge library containing the secrets of nature. And all he could do is read the first chapter in the first paragraph of the first book.
Right. You brought up music. What has been your relationship with music? And you use it as an analogy to help talk about string theory, and we're going to get into vibrating strings in a second here. But have you ever dabbled in musical instruments or singing or anything like that?
That's right. I was in the Harvard band for 4 years. I play the trumpet and play the guitar. And when I talk about music, I really mean that music is rich enough to explain the diversity of the entire universe. How many notes are there? An infinite number of notes. How many melodies can you write? An infinite
Yeah.
number. So music is the only paradigm rich enough to explain the complexity of the universe itself. And it's all based on a string, the simplest object there
Mm.
is.
And do you still play any of these instruments?
Well, unfortunately, I live in New York City, and my Manhattan neighbors would scream and yell if I was to blast out with my trumpet at 4 in the morning. No, it's very difficult to be a musician in Manhattan.
Right. And so where do you get your artistic inspiration, would you say? Do you garner a lot of that through your work in science, or are there any other means?
Well, people ask the question about beauty. Beauty to an artist is very ephemeral and very, very personal, but to a physicist is very concrete. Beauty to a physicist is symmetry. Why is a crystal symmetrical? Because when you rotate it, it rotates into itself. So if I have a sphere, a snowflake, and I rotate them, they rotate into themselves. That's called symmetry. Well, the equations of physics are symmetrical. Einstein showed that if I rotate space into time, the equations remain the same. Look at E equals mc squared. Children talk about E equals mc squared. That if you rotate m, matter, into E, rotate the two, the equation remains the same.
Right.
So E equals mc squared is powerful because it unifies matter with energy. Now, we want a huge symmetry that unifies the universe into itself. And the only theory big enough to do that is string theory. The symmetry of strings is big enough. The music of subatomic particles is big enough to rotate the entire universe into itself. And that is remarkable.
Right. So and guys, you have to get this book because Dr. Kaku does lay everything on the line for string theory and how he feels about string theory at this point. You have to read it. I'm going to pull up a section right now, but quickly, Dr. Kaku, what is the easiest way you can describe exactly what string theory is? What's the short form?
If I had a super microscope and I could look at an electron, you would think that it's a dot. Nope. We think an electron viewed up close is a rubber band. And if I twang that rubber band, it turns into a different note we call a neutrino. And if I twang it again, it turns into a quark. So this, for example, is an electron. This could be a neutrino. This could be a quark. So how many particles or notes are there? An infinite number of resonances or notes. So therefore, what is physics? Physics is the harmonies you can write on these vibrations. What is chemistry? Chemistry is the melodies you can create when these strings bump into each other. What is the universe? The universe is a symphony of strings. And then what is the mind of God? The mind of God is cosmic music. Music resonating through hyperspace. That is the mind of God.
Interesting. Okay, so now let's look at I want to go to page, for anyone that has the book, it's page 161, Criticisms of String Theory. And I will do a quick reading, quick quote from the book. There are several main criticisms that have been leveled at string theory. The critics have claimed that the theory is all hype, that beauty by itself is an unreliable guide in physics, that it predicts too many universes, and, most important, that it is untestable. How do you approach these challenges?
Well, let's take a look at the testability, first of all. There's now a crack in the standard model, which does describe subatomic particles. Just 2 weeks ago, people are now saying, aha, maybe, just maybe, this is because we're now talking about higher octaves of the string. We are the lowest octave. We are the lowest vibration of the string. If Einstein had never been born, I repeat, if Einstein had never been born, we would have discovered general relativity anyway, because it's nothing but the lowest vibration of a string. Einstein is for free. Think about that. Einstein's for free. Now we have the first plausible test of this theory coming out of Chicago at Fermilab and coming out of Switzerland with the Large Hadron Collider. And that could signal the coming of the string. And then there's dark matter. Dark matter makes the most of the universe. It holds the galaxy together. What is dark matter? That's beyond the standard model. Dark matter, we think, is nothing but the next octave. That's all it is. There's a higher octave of the string, and that we think is dark matter. So I think we will test the theory. All great theories are testable. As Carl Sagan liked to say, remarkable claims require remarkable proof. And I think in the coming years, we will have more and more evidence that, yes, these are higher notes, higher resonances of the string. And also, some people say that beauty is not a guide. Well, some beautiful theories are wrong. Let's be honest about that. Beauty by itself is not enough, but beauty with experiment. It turns out that all great experimental theories ultimately have a symmetry. So not all theories are correct, but all correct theories are symmetrical. And that's why I'm positive that this is the way to go.
Interesting. So a couple technical questions. In superstring theory, so the 6 spatial dimensions are wrapped in these Calabi-Yau manifolds. Is that correct?
That's right. Calabi-Yau.
With 10 to the power 500 or more varying topological representations. So is that a problem for a fundamental theory of everything, that there are so many of these variations?
Not really. Take a look at Newton's equations. How many solutions of Newton's equations are there? Well,
almost an infinite amount.
An infinite number.
Right.
A billiard ball, a marble, a cannonball, a rocket ship. It depends on the initial conditions.
A kiss.
You have to tell me. You have to tell me that we're analyzing a billiard ball today. rather than a rocket ship. Now, a theory of everything is a theory of the universe. Therefore, each solution of string theory entire universe. How many solutions are there? An infinite number, just like Newton would say there are an infinite number of solutions to Newton's laws of motion. Now, the difference is at the beginning of time, we're talking about the universe as it's being created. A baby picture of the infinite universe is what we need. We don't have that. We don't know what the initial condition was of the universe. And that's why we want to launch a telescope called LISA in outer space. It's a gravity wave detector which will detect radiation from the Big Bang. In other words, we'll have baby pictures of the infant universe as it's emerging from the womb, and then maybe it's attached to an umbilical cord. Maybe we'll find evidence of an umbilical cord attached to our infant universe as it emerges from the womb. That could also prove string theory.
Interesting. If we do find vibrating strings, where are we going to find them on the logarithmic scale?
Well, of course, they're going to be very, very energetic. The higher modes, we're talking about the energy of galaxies. So we don't expect to find we don't expect to find the higher resonances anytime soon. But today, we are the lowest vibration. We are the lowest vibration of these universes. Mm-hmm. Now, some people believe in what are called wormholes, that maybe there's a passageway to these other universes that could then confirm this theory. So Einstein gives us this picture that the universe is a bubble. We live on the skin of the bubble, and the bubble's expanding. That's called the Big Bang theory. But then the next question is, what does string theory say? String theory says there are other bubbles out there. Mm-hmm. And when these other bubbles bump into each other, that's the Big Bang. So the Big Bang could be the collision or the bifurcating of universes, parallel universes in a bubble bath of universes. And then I know you're going to ask me the next question. The next question is Elvis Presley still alive in a parallel universe? Quite possibly, yes. The king could still be belting out those hits, but in a parallel
But it's a different
universe.
king, right? It's not the same.
It's not exactly the same, but right. It looks very close to the king.
Right. So when we're thinking about a Planck length, what on the Planck scale, whereabouts would we find those strings? Like, how deep do we have to look? The Planck length being at, I think it's 10 to the negative 35th power. Whereabouts are we finding it on that scale? Where will we see these strings, do you anticipate?
Well, the size of the string is incredibly small, 10 to the minus 33 centimeters. Okay. So we're not going to see these strings anytime soon. Some people say, why don't we just get a microscope and just resolve it once and for all?
Right.
These strings are smaller than the wavelength of light. Therefore, light itself is too big in order to see these strings. So we have to look at the effects of strings indirectly. The fact that we have so many particles fits the scheme of vibrating strings. So I think that if we could really solve the theory from first principles, we could calculate with it. We could calculate the mass of the proton from first principles, the mass of the neutron, and I think that would settle the argument right there. A theory of everything is also a theory of ordinary energies. So we'll be able to calculate the mass of the proton from first principles. That is one of the goals of string theory.
Have you ever thought of an instrument that we might be able to create that allows us to observe strings? Like, is there a way we can, I know it's hard because observation tends to require light, but I don't know. Have you ever thought of this? Is there anything hypothesized?
Well, most of physics is done indirectly. Like, for example, how do we know what the sun is made of? No one's been to the sun. Mm-hmm. We've never had a piece of sun material on the earth. So how are we so confident that we know what the sun is made out of? Because we look for echoes from the sun called sunlight. And by analyzing sunlight in a prism, we say, aha, hydrogen. Hydrogen is what the sun is made out of. Same thing with strings. We cannot see the strings directly, but we can see echoes from the 11th dimension. And that is the theory. And what are these echoes? As I mentioned, dark matter, this mysterious matter that pervades the galaxy, holds the galaxy together, and also deviations from the inverse square law. When you were in high school, you learned about Newton's theory of gravity. The gravity gets weaker the farther you move. How much weaker? You double the distance, it's 4 times weaker. But if space is 5-dimensional or 6-dimensional on a tiny scale, it drops to 0 even faster when you separate two particles. That's measurable. And so we can even measure deviations from Newton's laws in your living room.
Right.
We haven't done that yet, but that's been proposed.
Right.
So what I'm trying to get at is indirectly, we can see evidence perhaps of string theory. And the European Space Agency and NASA are thinking about launching a new satellite called LISA, Laser Interferometry Space Antenna. It's a gravity wave detector in outer space. 3 million miles across. It is the biggest machine of science ever built. And it will pick up baby pictures of the infant universe. Wouldn't that be great?
Yeah, definitely.
And that could settle the question too when we calculate the characteristics of the baby universe as it's being born.
And Lisa's my mother's name, so all the better. So let's talk dimensions. Let's imagine for a second we find ourselves in 11-dimensional hyperspace, meaning the theorized space that our universe is expanding into. We are sitting in a spacecraft that allows us to survive, first of all, and sit in observation of all 11 dimensions. What do we see? If Da Vinci was there with us, say it's me and you, Dr. Kaku, with Da Vinci, and he looks out into 11-dimension hyperspace, what would he paint?
Well, first of all, we cannot directly visualize these higher dimensions because evolution only protected us against 3-dimensional tigers, 3-dimensional lions. We never had to fend off 5-dimensional tigers or 7-dimensional lions. So our brain is not big enough to visualize these higher dimensions. But artists have tried to do this. The most prominent is Salvador Dali. Salvador Dali was fascinated by the fourth spatial dimension. He visited Brown University's math department, pumped them from all information, and then he drew a picture. The picture of Jesus Christ crucified in the fourth dimension. Go to your history books, go to your art books, Google it, Hypercubicus crucifixion, the crucifixion of Jesus Christ in the fourth dimension.
Interesting.
Christ crucified on a tesseract. And then Salvador Dali wanted to represent time as the fourth dimension.
Right.
So he drew melted clocks. Why were the clocks melted in Salvador's paintings? Because clocks represent time and they're melted, representing the distortion due to, let's say, relativity theory. So great artists have tried to represent this. Now, when I was a child, I asked myself the same question. And I was at the Japanese tea garden in San Francisco looking at the fish. The fish swim in 2 dimensions. They can go forward, backward, left and right. But anyone who talked about up was considered a crackpot fish. I imagine there was a scientist in that pond. And that scientist fish would say, bah, humbug. There's no such thing as a 3rd dimension. The pond is the universe. The pond is 2-dimensional. And I imagine as a child reaching down, grabbing the fish, lifting the fish into the 3rd dimension. What would the scientist fish see? He would see beings moving without fins, a new law of physics. Fish breathing without water, a new law of biology. And today, we physicists believe, not all of us, but many physicists believe, that we are the fish. We live in 3 dimensions. Forward, backward, left, right, up, down. And anyone who talks about a higher dimension is considered a crackpot. Until now. Now with string theory, we are center of gravity in many physics departments. We realize that yes, 3 dimensions may not be enough. All the forces are unified in 11 dimensions.
Interesting. And just to poke a little bit more at my example, if Da Vinci had an apparatus that allowed him to see all of the 11 dimensions, what do you think he would see?
Well, unfortunately, our brain cannot do it. Now, your laptop can do it. If you
Right.
ask your laptop to visualize 11 dimensions, no problem. Your laptop regularly calculates an n-dimensional space. But sorry about that, you know. Salvador Dali, he tried to get cross sections,
Right.
slices of the higher dimension, and that's the main reason why Salvador Dali's paintings are so great. They represent slices of higher dimensions, but not the full dimensions by themselves. Our brains are not capable. Sorry
Interesting.
about that.
Okay, a couple quantum mechanics questions. If you had to place a bet, what is dark energy? I mean, most of our observable universe is dark energy. It seems. What is it?
Well, first of all, there's dark matter, which is that which keeps the galaxy together. And then there's dark energy, which is the energy of the Big Bang. So, what is dark matter, which makes up most of the matter of the universe? We think it's a higher excitation, a higher octave of the string called the photino. The photon, that is light, has a partner, and the partner is the photino. It is invisible, it has mass, and looks just like dark matter. So one day we will capture dark matter in the laboratory. We are moving in a wind of dark matter right in your body. A wind of dark matter goes
Hmm.
through your body even as we speak. One day it'll smash into a proton and cause a spark. We will photograph the spark and say, aha, we now know the properties of dark matter. That could happen any day now.
Right.
We have dark matter detectors all over the earth. Any day now, somebody could say, aha, we've detected a collision of dark matter with ordinary matter. We'll test string theory this way.
Right. Is the Planck length truly the maximally small length that can be measured, or can we hypothesize a way to go deeper?
Well, yeah, we think that the Planck length is the smallest length. The Greeks used to ask a question, when things move, how many points do you move through? An infinite number of points from A to B? If so, it takes an infinite amount of time to go through an infinite number of points, and therefore nothing could move. And so Zeno, the great Greek philosopher, proved that motion was impossible. Nothing could move because you have to move through an infinite number of points to go from point A to point B. Well, that was before Newton and calculus. With the coming of calculus, we figured out that you can, in fact, move through an infinite number of points in a finite amount of time. But that leaves open the question, is there an ultimate unit of length? We think so. It is the Planck length. It is the length of a string.
Mm, the length of a string. Interesting. Uh, okay, I wanna jump to a couple more categories here. Climate change for a second. Lawrence Krauss just released a new book, The Physics of Climate Change. I read it. I thought it was a fantastic collection of the data available, and he's got his kind of thoughts at the end of what it means. It is a great physical account of the Earth's changing climate. I don't see any probable climate catastrophes that couldn't be overcome by engineering. Do you agree with that?
Well, I think it's a race against time. On one side, we have the Earth, which is heating up. We see that by satellites, that the Earth is heating up. On the other hand, we have environmentalists pushing different kinds of technologies. So some of them are worth looking at. The problem with solar power, for example, is something that most people neglect. When the sun doesn't shine and the winds don't blow, solar detectors, solar panels are useless. The problem is the battery. Everybody forgets this. We need a super to store energy when the sun doesn't shine and the winds don't blow. That is preventing us from unleashing the solar age. The next problem is fusion power. I think they're out of it without using oil or coal, and that is fusion, the power of the sun. Now, think about it for a moment. Fusion reactors use seawater. Seawater, not coal, is the engine that drives fusion reactors. A meltdown is practically impossible in a fusion reactor, and that's Mother Nature's choice. Mother Nature doesn't use uranium. Uranium for Mother Nature is unnatural. Not what nature wants is a fusion plant to generate unlimited power. The catch is it doesn't exist yet, but in southern France, the European Union is betting on the ITER fusion reactor, which will be turned on in a few more years, and that could be the prototype for a fusion era when we use the power of the sun on the earth. That could be the ultimate cure for the greenhouse effect, if we can only get it off the ground.
The Chinese have started firing up these mini suns. They're essentially calling them. Are those the same type of reactors? Have you seen those?
No. So far, the problem with fusion is the fact we use magnetism to squeeze the gas, and magnetism has two poles, North Pole and a South Pole. It's very difficult to squeeze a North Pole and a South Pole.
Yeah.
We do it by making a donut out of magnetism and squeezing the inside of a donut called the tokamak. That's how we do it. Very clumsy. Mother Nature does it because gravity does not have a North Pole and a South Pole. There's only one pole for gravity, and that's why stars are formed by themselves. We don't even have to think about it. Gravity compresses stars all by themselves to create fusion. On the Earth, we have donuts, and donuts are much more difficult to compress than a sphere.
Right. And yeah, okay, interesting. So I want to take everyone to page, I believe it's 208 before the conclusion. And quote from the book: "One day our descendants will master the Planck energy, the energy at which space and time become unstable, and use their powerful technology to escape our dying universe." This does, end quote. This does seem inevitable to me. Could you explain why we must eventually escape?
There's something called the second law of thermodynamics. In a closed system, everything rots, everything falls apart, everything decays, everything becomes random. Now, our universe will also obey the second law. One day, the stars will blink out. The universe will consist of dead stars, dead neutron stars, and black holes. Temperatures will be near absolute zero, and life as we know it will die. Physics is a death warrant for all intelligent life in the universe. However, there's one escape clause. One escape clause. I said that in a closed system, everything must eventually die. But let's say the universe was open. In other words, there's a gateway. There is an escape hatch. There's a lifeboat. Trillions of years from now, we'll be so advanced that we'll use the Planck energy to open a gateway, a wormhole, to a warmer universe. We will escape this dying universe of ours in an interdimensional lifeboat and go to a warmer universe, and then we'll go on to mess up that universe as well. So we'll have another greenhouse effect in the other universe, and we'll start all over again. Isn't that great?
that's, that's super interesting. It's both inspiring. It's bittersweet.
We may have no choice. All
Right.
intelligent life will ultimately die when the universe itself dies.
Right. Well, my third book is going to be my stab at a theory of everything, and yeah, I'm calling it the state of potential theory. So perhaps I'll email you about that when I'm ready to unveil it, and I'll see what you think about that. To finish off, I want to ask you this question. It's a question I ask a lot of my guests. If this was your final message to humanity right now, what would it be?
Well, I would say that the universe is a chess game, that the greatest minds have figured out how pawns move, how bishops move, as I mentioned. And now we're on the verge of becoming grandmasters of this game of chess, to be able to manipulate space and time to our will, so that we're not necessarily going to die when the universe dies, but we will have an answer to the question. If the universe is expanding, what is it expanding into? If there's a black hole, is a white hole at the other end? Are there parallel universes on the other side of a wormhole? Is time travel possible? So I say, let us continue to work on this theory, because it'll answer the deepest questions of space and time. Questions about time travel, interdimensional gateways, the multiverse of universes. This is the ultimate goal of a theory of everything.
Well, Michio, it's been one of my greatest honors of my career to have a conversation with you today, and I really
Oh,
appreciate you,
thank you.
coming on the podcast. I look forward to you engaging with your fans later about your new book in the Pangburn Q&A. But for now, I will let you go and sign off, and we'll talk to you at 5 p.m. Pacific time later.
Okay.
Thank you very
Talk to you
much.
then.
Yeah.
Hey, Vancouver, let's talk physics and more. I'll be at the Vancouver Playhouse October 13th talking about my new book, The Edge of Knowledge, along with Travis Pangburn. And we'll talk about a lot more than just that. We'll talk about life, the universe, and everything. And we'll also maybe talk about atheism a little bit. I notice I have my God detector, and I keep looking at it every day and notice there's still no God. So maybe we'll talk about that as well. But mostly I want to focus on the mysteries of the universe, and we'll have a Q&A so you can ask questions. And I hope to have a great time out there. See you October 13th at the Vancouver Playhouse. Take care.